This is a graph that's talking about the Haber-Bosch process and how efficient it could be. You will notice for every one of these curves that you get more yield as you increase the pressure. Well, that's not actually a surprise now that we know about Le Chatelier's principle, that there are 4 gases on this side and only 2 on this side. So if I increase the pressure, I'm going to shift it to the products and I will end up with more ammonia. Every one of these curves is increasing in value as you increase the pressure. But pressure isn't the only thing that is going on. Temperature affects K. K is a function of temperature in some way. I do know that delta G is both delta H minus T delta S, as well as that delta G is our new minus RT natural log of K. We are going to use those facts in order to derive something called the Van't Hoff Equation. So let's talk about this being at 2 different temperatures. Whatever the temperature is, I can say that delta G at temperature 1 is minus R T1 times the natural log of K at that temperature T1. Similarly, delta G at T2 is going to be minus R T2 times the natural log of K at T2. Since I'm not in a mood to divide logarithms, I'm going to rearrange this to say the logarithm of this, and I'm just going to call it K1 now and say that it is associated with temperature 1. Subscripts on subscripts starts looking pretty weird. This is negative delta G at T1 divided by R T1. And the same idea here. The natural log of K2 is going to be minus delta G at T2 and RT2. Let me subtract the logarithm like this. That's the same as doing a division in normal space. So if I take this and subtract that, that's the same as taking this and subtracting that, right? So minus delta G of T2 over RT2 minus a negative delta G of T1 at RT1. This is the same thing as saying natural log of K2 over K1. And this, well, gee, since that's positive, I'll write it first because that just seems a lot nicer. Delta G of T1 over RT1 minus delta G of T2 over RT2. That still doesn't look like the Van't Hoff equation. So what are we going to do next? Well, I'm going to use the fact that delta G equals delta H minus T delta S. This is why there is a delta G at a temperature, because there's a T in here, right? So that means I'm done messing with this. I only have to deal with this. This one will be delta H, and I will go ahead and call it 1 minus T1 delta S1 over RT1. And this would be delta H2 minus, and remember this minus is referring to the whole thing here, T2 delta S2 over RT2. This is a little bit of a lie, but we are going to make a not too bad assumption that delta S does not depend on temperature. Once we say that, when I break these up, I'm going to be able to do something more interesting. And I'm not going to put a 1 on it anymore, because I'm going to say delta S is invariant to that, RT1. Let me just cancel those T1s out then. This is just minus delta S over R. And then I will have minus delta H2 over RT2. And since I've already figured out that the T2s are going to cancel, I will just write it as delta S over R. Here's a minus delta S over R and a plus delta S over R. So this and this end up canceling each other out because delta S is very insensitive to temperature. That means that I'm left with the natural log of K2 over K1 being equal to delta H. I'm also going to say that that does not depend on T. If you get really vastly different temperatures, this is not going to be correct. But if you're talking about, hey, it's staying in the same phase and we're changing the temperature by only 100 degrees, good enough. At that point then, we can just drop the 1 and the 2 on this. Well, that means I have delta H, and I have R, and I have 1 over T1 minus 1 over T2. And that is your Van't Hoff equation, which looks very suspiciously like the Clausius-Clapeyron equation that we saw before. That was vapor pressure at 2 different temperatures and how they were related. Let's stop and think about that for a minute. The vapor is in equilibrium with its liquid component. So the Clausius-Clapeyron equation is also an equilibrium equation. So they look alike because they're based on the same sort of physics where you're talking about an equilibrium that exists. In one case, it was for vapor pressure. In another case, it's for the speed of a reaction. Okay, so what does this have to do with the rest of this? These are different temperatures, right? And these are different yield curves based on temperature. We've looked at this in terms of kinetics. We said how fast a reaction will occur is going to depend on the temperature. If you give it higher temperature, you're going to be able to increase the speed at which it reaches equilibrium. That sort of sounds like we should just infinitely increase both the pressure and the temperature to make ammonia as quickly as possible. But we also find out, because of the fact that this is exothermic, that means heat is a product. And if I increase the temperature, I'm going to be, according to Le Chatelier, pushing it back this way. So what we have here is that the lower temperature will favor the yield on the ammonia, but it's going to slow down how fast you can make it. So in point of fact, when they make ammonia commercially, they actually do it in this range of temperatures. Not this, because it's too slow. Not this, because quite honestly, when you get to that sort of temperature, you're depressing the yield, but you're also having the problem of trying to keep it at that temperature. The hotter you're trying to keep it, the more waste energy there will be. So it's found that if you stick in this region, you will increase how quickly you make it without making it exorbitantly expensive to run the plant that creates it. So this starts to talk about also the economics of a particular temperature, as well as its efficiency.